And if we scroll all the way up here again, it actually already says what is wrong. It states that to provide a detailed explanation, Copilot would need to see the specific implementation of the calculate total price method we're referring to. So what that means is that Copilot Chat does not take into account what is open in the IDE. We need to explicitly refer to it. And we can do that with the hashtag symbol. We can refer to the accounting service class, and that will definitely help. But I want to show you yet another thing you can do here, and that is take the complete solution into account. So I'm now going to ask it to explain calculate total price on accounting service, and I'm going to reference the full solution. Now, referencing a complete solution is typically something you would do when you want code suggestions that involve a bunch of files, typically things that touch upon different layers in your architecture. But even though we don't have that in our library, by referring to the solution like this, Copilot will be smart enough to know that it has to look for calculate total price on something named accounting service, and by referencing the full solution, the accounting service file is referenced as well. So therefore, this should give us a better result. And that is already looking a lot better. What we see being generated here is effectively a correct explanation of our calculate total price method. If you look at the process, Copilot was smart enough to know we first initialized the total price, then ran through all the orders. It knows that the orders list is a list and that it is named orders. It knows that the variable name we chose for an order line is order line, and it knows that it should look at the amount and the price here. So that is already quite impressive, right? Let's try one more thing. I'm going to ask it to optimize the calculate total price method. So let's send the optimize command. And Copilot here suggests us to switch to link. It explains why it considers this an optimization, and what's interesting, it also explains some potential trade-offs. Now, whether or not this is completely correct is something we still have to validate. Don't just take what Copilot says as the single source of truth. The reason I wanted to show you this is to show you that all I've sent here was the optimize command. I didn't have to refer to the accounting service file or to the calculate total price method or anything like that. Copilot automatically knew that I was talking about this method, and that's because it takes into account the previous things we chatted about with Copilot. So it knows that the last thing we chatted about was the calculate total price method, and if I then ask for optimization, it knows or thinks that it's that method that I want to see optimized. If we click preview here now, we actually get a preview of the changes right in our code base. And there we go. Those were our first steps into using Copilot. Personally, except for simple things, I prefer working with the Ask Copilot inline window, or even more often with Copilot Chat. But that is, of course, pure personal preference. Use whichever approach you like. All these things that we fed to Copilot, and by that I mean the code comments, the command, the code itself, all of that is part of a prompt. We'll dive deeper into this in the next module, because there's a lot more things we can do to get Copilot to generate what we need. Those things are called prompt engineering. But I think that before we go ahead with that it is a good idea to learn a bit more about how Copilot works underneath the covers, because understanding that up to a certain level will definitely help in writing better prompts and thus getting better results from Copilot. Let's talk about generative AI and large language models. Generative AI, or Gen AI, is artificial intelligence capable of generating original content. In our case, original lines of code in response to prompts. The way it does that is by leveraging large language models. Those are models that have inspected typically human written content and use that as a basis for generating new content. A prompt in this case can be seen as whatever is fed into the model. This can be natural language, it can be code, it can be additional context, and so on. We will detail this much more in the next section, which covers prompt engineering. But anyway, those prompts are fed into a large language model or LLM. And content almost magically comes out. Many different types of LLMs exist. LLMs that are trained on code, like GitHub Copilot. General purpose LLMs that are trained on natural language. ChatGPT is a good example of that. And then you have LLMs specifically catered to mathematics, to images, to generating music, and so on. And there's much more than just this. But let's take a step back before we detail the LLM a bit more. AI is a pretty broad term. You often see terminology like AI, machine learning, deep learning, LLMs, and so on thrown together, while they all have their own specificalities. So let's first clarify that a bit, and let's start with AI. It means artificial intelligence, and it is a bit of an umbrella term. It refers to the theory and development of computer systems capable of performing tasks that historically required human intelligence. And there's many tasks like that, as you can imagine. Recognizing speech, making decisions, identifying patterns, and so on. Those are all common tasks that require human intelligence, or at least that used to require human intelligence. As it's such a broad term, it encompasses various techniques: machine learning, deep learning, natural language processing, computer vision, speech recognition, and LLMs are all under the umbrella of AI in one way or another. For us, as we're dealing with LLMs, the ones of importance are machine learning, deep learning, and natural language processing next to LLMs. So let me start with machine learning. That can be seen as one of multiple subsets of AI. The idea for regular machine learning is that you've got a set of statistical algorithms that learn from data that is labeled and generalize what they've learned to new data, so to data that is not labeled and that hasn't been inputted before. Feed a machine learning algorithm 1,000 pictures of cats in which you say which part of the picture is a cat, and a machine learning model should be able to tell you which part of an image it hasn't seen before and contains a cat is the cat. A good example of machine learning is natural language processing, and that is the understanding and interpretation of human language by computers. So, natural language processing as example of machine learning. And then we have deep learning. That again is a subset, but this time it's a subset of machine learning. Deep learning models do not learn from labeled data, but from unlabeled data. And to do that, it uses neural networks that are inspired by the human brain. They rely on massive data sets to efficiently generate the intended outcome. It also, by the way, turns out that it's much more efficient to recognize cats in pictures than regular machine learning. Large language models, lastly, are a specific type of deep learning. They are models designed for language-based tasks. Large in this context, by the way, means two things. One, it refers to the sheer scale of the models. So the scale, the size of the neural network itself. And two, it refers to the large amount of data that is fed into such a system to train it. Language in this context is a broad thing. Code, music, images can all be languages that you train a large language model on. Large language models are used a lot in generative AI. They are used to generate content in the language they are focused on. In the case of GitHub Copilot, that is obviously mostly code. By the way, in case you're wondering, GPT, like in ChatGPT, means Generative Pre-trained Transformer. and it too is a type of large language model. Alright, with that you should have an idea of how this terminology relates to each other, and what it is and what it isn't. But how does that neural network in LLMs work then? How does it look? Where does it come from? Well, step 1 is feeding it data, input, large amounts of input. That data, that input, is then tokenized. And tokenization means breaking down the input in smaller units, like words or parts of words. These are represented by numerical representations that can be processed by the model, and that includes the order in a sequence. From those, links between those tokens are formed. The process through which that is formed is called self-attention, so it is self-learning in a way. While forming these links, many potential parameters are taken into account. To give you an idea of the vast scale of these, in GPT-3 there are 175 billion different parameters, like weight and biases between tokens, that are potentially taken into account. Next to that, there are 96 layers of connections between tokens stacked on top of each other. Obviously, I'm not going to draw all of them, but you notice that this is a huge amount of layers and connections. It's actually hard to imagine how huge that is, but like that you get this neural network. And this is GPT-3 I'm talking about. GPT-3 is something from the past. At the moment of recording, we're at GPT-4, and that's just GPT-3 I'm talking about. With every new generation, the amount of parameters and layers potentially multiplies. Like that, you get this neural large language model, this neural network. This is, by the way, a very simplified explanation, but it does already make it a little bit more tangible, I hope. Okay, so we've got this network and we've trained it. How do we get to an outcome then? Well, the data you input, the prompt, is first tokenized, and then using its neural network with all the pre-trained data and links and connections between tokens, the large language model tries to predict the next token by following those connections across all those layers, given the previous token and the input. And that apparently works impressively well. So that is an LLM, a large language model. But it does seem to have some overlap with an NLP, a natural language processor, right? They both seem to have to do with understanding inputted text and providing understandable output. Each have their own strengths and weaknesses. NLPs, natural language processors, tend to be highly accurate and efficient for specialized tasks with relatively low computational demands. Large language models then are better at generating human-like text, coherent language output, and a wide spectrum of tasks. Yet, they also tend to lead to more inaccurate results than natural language processors. So when you're building an AI assistant like Copilot, what should you do? Well, let them work together, of course. Use NLP for bridging the gap between human language and machine understanding, and potentially use that as part of the input, the prompt, for the large language model. And that is how this works. Well, at a high level at least. I'm not going to pretend that I understand all the details of this. That definitely goes beyond what I know and can understand, to be honest. But it does help to have a bit of an idea, right? And with that, it's time for the summary